Okay, in this presentation we are going to look at an actuarial example. This features the negative binomial distribution, which is used to characterize or model Poisson-Gamma mixtures. Okay, so let's look at the question here. The number of claims in a year for an insured from a large group of insured is modeled by the following. Probability of x equal x given lambda is equal to e to the minus lambda times lambda to the power of x divided by x factorial, where x is equal 0, 1, 2, 3. So essentially that is a Poisson distribution there. So that's the first part of our Poisson-Gamma mixture, the Poisson distribution. Now the thing about the Poisson-Gamma mixture is it allows the gamma to be a random variable here, which is the case here. The parameter lambda varies from insured to insured. However, it is known that the gamma is modeled by the following density function. Okay, g of lambda equals 32 times lambda squared times e to the minus 4 lambda, where lambda is greater than 0. Okay, so an insured is randomly selected from a large group of insured. Determine the mean and the variance of the number of claims for this insured in a given year. Okay, so what we have to do there is check that this random variable lambda, we have to check does it have a gamma distribution. Okay, so obviously it does, because that's the whole point of the question, but what we have to do is double check it there. So g of lambda equals 32 times lambda squared times e to the minus 4 lambda, where lambda is greater than 0. Okay, so this is the probability density function of the gamma distribution here. I probably should have written that in, but this is the gamma distribution essentially. Okay, I just paused it there. I just wrote some stuff in. So this is the gamma PDF function, and this is denominated in terms of t. Okay, so f of t equals 1 over n minus 1 factorial times lambda to the power of n times t to the power of n minus 1 times e to the minus lambda t. Now remember, the gamma distribution has lambda as a parameter. Okay. Now, up here, what we have is the Poisson mean as a parameter, and that's also denominated as lambda. So what I've just done here is I've re-expressed that as a function of t. So g of t equals 32 times t squared times e to the minus 4t. So now when we're talking about lambda, specifically what we're talking about is the gamma parameter lambda and also the gamma parameter n. Okay, so what we have to do is just match up n and lambda, and just to sort of see, does this fit with our notion of the gamma distribution. So what we have here is e to the minus lambda t, and if we look at this here, what we have here is e to the minus 4t. Okay, so that means for the gamma distribution, lambda is equal to 4. Here, let's look at t to the power of n minus 1. Up here we have t squared, so that means that 2 is n minus 1. Okay, sorry, just meant to color that in there, it's not working. So that means that n is equal to 3. So we have our two parameter values for the gamma distribution. Lambda is equal to 4 and n is equal to 3. Okay, and what we can do is just check that to see does that work out based on this gamma PDF. So 1 over n minus 1 factorial is 1 over 3 minus 1 factorial. Okay, just park that for a second. That will just work out to be 1 over 2 factorial, which is 1 over 2. Lambda to the power of n is 4 to the power of 3, which is 64. Okay, t to the power of n minus 1 is t to the power of 3 minus 1, which is t squared. And e to the minus lambda t is e to the minus 4t. Yeah, and when we have 64 divided by 2, we get 32. Okay, so that matches up with what we have there. Now again, just to reiterate the point, this is deliberately confusing that we have lambda as the Poisson mean here and a different lambda down here as the gamma distribution parameter. But that's something you just have to live with. Okay, and what you do there is just re-express it there. Just don't get yourself caught in traps. Okay. So now the probability mass function. So essentially this is where the negative binomial distribution comes in. Okay, so this is the probability density function, sorry, the probability mass function of the negative binomial distribution. So this is a definition we're probably going to be using shortly, or actually we're not, we're asked for the mean and the variance. But in other questions we'd be asked for the probability mass function or calculations based on that. R is the number of successes, that's the parameter values, R, and K is the number of failures, and P is the probability of success. Just as a quick remark, there are multiple specifications of the negative binomial distribution. So there's one that's particularly used when in the context of Poisson-Gamma mixtures, this one here. But just be careful, okay, about which is which, okay. So we can view the negative binomial as a Poisson random variable with a rate parameter lambda, where lambda is itself a random variable. It's distributed as a gamma distribution with a shape parameter, alpha, also known as lambda, and beta, also known as n. Okay. Now, actually, you notice that I'm being deliberately obtuse here because the shape parameter of the gamma distribution is typically, or can be typically, written on in terms of the parameter values, shape parameter alpha and rate parameter beta, but I went for n and lambda particularly to be difficult, so that you pay attention to notation. The probability mass function can be also specified as follows. Okay, that actually helps in the context of what we're doing here. So we'll actually probably use this probability mass function in wherever we need it when we're dealing with Poisson-Gamma mixtures. Now, so we have n and we have lambda. Okay, so what we might need is the parameter values for the negative binomial distribution, which are r and p. So essentially, it's r is the n value, the value from n for the gamma distribution, the rate parameter, and the probability of success is 1 over lambda plus 1, which is the probability of success. That is 1 over, that is the shape parameter. Sorry, I'm just lost for words. Okay, so the expected value of x is, for the negative binomial distribution, is n divided by lambda, and the variance is n divided by lambda times 1 plus 1 over lambda. Okay, so the variance of the negative binomial distribution is greater than the mean, and in the Poisson distribution is equal to the mean. So the question actually asks us just for the expected value in the variance, so we don't have to get too worried about other things like the probability mass function. It's good to know, but it's not part of this question. So we're asked for the expected value of x of the negative binomial distribution, which is n divided by lambda, 3 over 4, which is 0.75. And the variance of x is n over lambda times 1 plus 1 over lambda, 3 over 4 times 1 plus 1 quarter, and that is 0.75 times 1.25, and that is 0.935. Okay, we'll leave it there.